Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 1st, 2025, which was about 8 days ago. The standout result is that reinforcement learning for visual tool use delivers state-of-the-art performance on perception-heavy benchmarks, with ReVPT 3B and ReVPT 7B beating instruct models by 9.03% and 9.44% on CV Bench. The paper is titled Reinforced Visual Perception with Tools, and the implications for model training are quite significant. In brief, this study trains multimodal language models to invoke object detection, depth, edge, and zoom tools using a group relative policy optimization approach, avoiding costly data curation while generalizing better than supervised traces. So Figure 1 makes a simple point. Reinforcement learning for tool use lifts accuracy on perception-heavy benchmarks while keeping broad skills intact. The two radial charts compare 4 variants for 3B and 7B models, where longer spokes mean higher scores. Group relative policy optimization means the policy improves by comparing candidates within a group, which stabilizes learning. The dark blue bars dominate on CV Bench and several others, signaling consistent gains. Alright, Figure 2 shows how the model solves tough perception tasks by thinking step by step and calling the right visual tool. Visual tool use means the model can request a specialist like object detection or depth estimation to analyze the image, then reason over the result. The left panel handles counting with object detection, the middle resolves distance using depth, and the right infers spatial relations, which boosts accuracy over GPT 4.1. So Figure 3 explains how the system learns to call vision tools and turn their outputs into better answers. The top block shows a local tool controller that dispatches depth, object detection, edge, and zoom services, which means external programs analyze the image and return results. The bottom workflow illustrates group rollouts scored by a rule-based reward, so higher scoring trajectories push the policy to improve, while a KL penalty keeps it stable. This pipeline enables adaptive, multi-step tool use during reasoning. So Table 1 lists the 4 visual tools the agent can call, which matters because each tool contributes a distinct signal the model can reason over. Open vocabulary means the detector can find objects from free-form text. The table specifies inputs and outputs for object detection, zoom in, edge detection, and depth estimation, so the training loop can parse them consistently. These standardized interfaces make multi-step tool use reliable. So Table 2 compares models across perception-heavy benchmarks and shows that reinforced tool use delivers the strongest average gains while keeping broad skills competitive. The key columns under CV Bench split tasks into count, relation, depth, and distance, which isolates where perception matters most. ReVPT 3B and ReVPT 7B top the non-commercial baselines and post the largest boosts on depth and distance. The deltas row highlights these gains clearly, so the takeaway is consistent improvements without sacrificing general benchmarks. Wrapping up, 2 takeaways stand out. Reinforcement learning with group relative policy optimization makes multimodal models reliably call vision tools, and that shift delivers clear gains on perception-heavy tasks, especially depth and distance. The broader implication is pragmatic. Small models get smarter by orchestrating specialist tools rather than scaling alone. Thanks for listening. I am Alex, signing off.